Chapter 2, number 55. You are driving through town at 12.0 meters per second when suddenly a ball rolls out in front of you. You apply the brakes and begin decelerating at 3.5 meters per second squared. A. How far do you travel before stopping? B. When you have traveled only half the distance as you found in part A, is your speed 6 meters per second, greater than 6 meters per second, or less than 6 meters per second? And part C. Find the speed of your car when you have traveled half the distance and hopefully verify your answer. Alright, step 1, as always, is draw a picture. So we'll do this, and we'll have our car at the start, and then the car somewhat later. We'll call this t equals 0, and we'll call this t equals some final time that I don't know. And we'll also say that this position is 0, and this is some final position that I also don't know, but is my point from part A, so that's what I'm going to try and get. Because of that, then we would have that the car starts with some initial velocity, which is v0, which is given as 12 meters per second. The other thing we'll want, of course, in here is that the car itself is moving. We want to talk about the halfway point. So part A, we want to find the final position, what we don't have, right? So we want xf. What we have is an acceleration, which I have not marked, so I should. That the whole time it's accelerating that way. So we have the acceleration during the whole time. We have the initial final velocity. We have initial position. We want a final position. But what we do not have and do not care about in this particular part of the problem is this guy. We don't really care about TF. So we're going to go and use the kinematic equation that does not have a time in it, which is v squared is v0 squared plus 2a x minus x0, that the velocity at any time squared is equal to the velocity at the initial time squared plus this correction factor. And for us, life is relatively easy because some of these things are 0. For instance, we end at a rate at 0, and we started our position at 0. So for the thing we want, in that case, our x is going to be xf. So we're taking our particular moment, right? The thing in blue is true at all moments, and the things in yellow are the values at our particular moment, and so we end up with 0 equals the initial velocity squared plus 2 times the acceleration times the final position, which can be solved over for the final position. Let's actually clear ourselves some room and get I've not used the board in a great way here, but we'll try it. So we end up with that xf is v0 squared over 2a with a minus sign out front. And I think what I'll want is a new board for this. We're going to want some more room to write and draw, so I'm going to scroll the problem off the screen. Of course, you have it in your textbook. And that leaves our picture and our current work. So to sort of reiterate and write more legibly, our final position is minus v0 squared over 2a which is minus the 12.0 meters per second quantity squared over 2. And then we need to be careful here because we're going to have minus the magnitude of the acceleration that was given. In other words, because it is decelerating, the acceleration is to the left, and it has a minus in front of it. So we get minus 3.5 meters per second squared. And we're happy with that because that means that our final position will have a minus on top and a minus on bottom and will turn out to be positive. In fact, it turns out to be 20.571, and then we check our units, meters squared per second squared over meters per second squared, and we see, as has happened several times, the second squareds cancel exactly, the meter squared cancels once, and we're left with, as we hope, meters. And then tracking our sig figs, it looks like we have at best 2 significant figures because of the 3.5, so I should really round this to 21 meters. I'm probably actually going to carry an extra place all the way through as we start doing some other stuff just to keep track of it. So there we are. So the first position, the car stops in 21 meters. Part B is sort of a thought process problem. Part C will be our verification of it. And they ask if when we reach the halfway mark, which we now know is at something like 10.5 meters, is the car moving at half of its original speed, less than half its original speed, or more than half its original speed. And the key here is to recognize that the average speed during that first half of the leg is going to be higher than the average speed during the second half of the leg because it's slowing down, so sort of duh. Because of that, since we're talking about covering equal distance but at a lower speed in the second half, then the time must be more. In other words, we're going back to the idea, as always, that the average velocity is the distance over the time, the change in distance over the change in time. So in the first half of the trip, in the first half of this, in the first half of XF, we have a greater V average. V average is large, so delta T is small. And in the second half, we would have the reverse. We'd have that the average speed is small, so therefore the time must be large. That tells us that it takes less than half the total time to travel the total distance, half the total distance, which means that there hasn't been as much time for the acceleration to be applied, which means we have lost less velocity during that first half of distance than we will lose during the other half of distance, which means we haven't lost 6 meters per second, therefore we're closer to 12. So the final thing is that the average during the first half, or actually I guess what we really should say, to be strictly true, what I really should say is at half the distance, the velocity is closer to 12. That is, the velocity is greater than 6. And then we'll verify now on the next thing, and hopefully when we actually get the velocity at the halfway distance, we will be able to figure out, we'll see that it's larger than 6. In fact, it will probably be, it'll probably be at 9. Here we're going to go back and use the same equation that involves no time, because we don't want time. What we know, of course, up here now is that the x1 is no longer unknown. Instead, it's half of the other distance. I'm going to take the 21, I'm going to treat it as 20.6. In other words, I'm going to put back a digit of significance because we're going to be doing some rounding and I don't want to over round. So I'm going to call it 10.3 meters because this was really 20.6 meters. Not really, but before we did our rounding. And we want to track that out. And then I'm going to fall back on the equation that does not have any time in it. So I'm going to fall back on the idea that v squared at any time is v initial squared plus 2a times the change in position from the initial moment. And again, we're going to pick the particular time, but now we're picking a different moment where we don't know v. That's going to become this thing up here that I called v1. But we do know that the initial velocity is still, or was, the 12 point whatever. And we still know that the initial position was 0. And so we're left with v1 squared is v initial squared plus 2a x1. And I know all these things, so I'm just going to put in for them. I'm going to say that v0 squared is 12 meters per second quantity squared. And then the acceleration is, as we remember, minus 3.5 meters per second square. It's that way throughout the whole problem. We're still going leftward or against the motion. And now we're imposing that we're traveling a distance 10.3 meters. And we throw that into our calculator. We get 144 meters squared per second squared minus 72.1 meters square per second square. Again, checking our units here, meters per second squared times meters is meters squared per second square, so we're still okay. That difference is 71.9 meters squared per second squared. And remember, that's v0 squared, so v0 is just the square root of that. Which turns out to be 8.479. And of course, the square root of meters squared per second squared is just meters per second. And then we really should round that, and since we only had 2 digits before, we really should round this to something like 8.5 meters per second. So not quite 9 I was expecting, but rounding to the right amount. And clearly more than 6. We are traveling faster than half our maximum speed because to recap, we reached the halfway mark in far less than the halfway time. So the acceleration has not had much time to take off velocity, so we have not reached our halfway velocity. We're somewhere between 12 and 6, in this case 8.5.